Hi folks, Damon here. So today I want to do a quick intro to data processing on AWS. One of the questions that I see coming up when folks first get started with analytics on AWS is just kind of how things work under the hood, right? There's a lot of different services you can use. They're purpose built for different use cases, but they do integrate in certain cases, right? Perfect example is Athena and the Glue data catalog. Those two services work natively together. When you create a table in Athena, it's stored in the Glue data catalog. So what I want to do, I just want to do a quick example of what happens when you run a query in Athena. And then I want to do a little bit of a deeper dive and hop over to Spark on EMR and see what data processing looks like when we're running Spark queries. So let's hop in. I've got a data set here in my S3 bucket. So I've got this Athena data set, and it is the DEA pain pills database. So the Washington Post made this data set publicly available. And you can see I've got a TSV file here that is 75 gigs. So pretty meaty TSV file. And I've also got a gzipped version of it, and that compresses down to 6 gigs, right? So this happens all the time. People send you compressed files because it's a lot easier to send 6 gigs than it is 75 gigs. So I want to show you what happens both when we query that raw TSV as well as the gzipped one. So the first thing that we're going to do, we need to create a table in Athena. And I've got this query all set up here to create my DEA pain pills TSV table. I've got the schema already all set up, and then we're just going to say row format delimited, tab separated, and lines terminated by a new line, and then there's the location of it in S3. So I'll go over to my Athena console here. I already created a database called intro to dataproc, and you can see that database over there. And now I'm going to go ahead and I'm going to create this table as well. So what this does, this in the back end is going to Glue and creating the table inside of Glue with references to the schema and the location on S3. And now I can simply go in here and I can do a select star from my TSV file, and I'll just do a limit 10. And you can see it's going, running the query, and that came back in under a second and only scanned about a meg of data. Now we can see some information about the file or about the data there. If I want to do a count star, for example, let's see what happens there. This will be a little bit interesting. So it goes and it runs again, and this will take a little bit longer to run, but it finishes pretty quickly too. But what we'll see when this finishes is that it's actually going to scan all 75 gigabytes of that file. So let's pause and let's talk a little bit about what's going on in the background with just those three SQL statements. So number one, the create table. Behind the scenes, Athena is going to your Glue data catalog and creating a table in the Glue data catalog. So if I flip over to the Glue console here, you can already see there is my pain pills table. And if I go and click on this, here is some information about that. It's got the location of it. It's got the input format. This is the text input format is the row input delimited. So Athena is populating this data catalog item with all the necessary classes to read the data, serialize it, deserialize it, and all that kind of stuff. And then here's the schema down here. So this is just referring to the actual file. I can go in here and I can actually change the schema in the Glue data catalog. So maybe I have this reporter DEA no here. I want to change that to number. I can go ahead and change this in the Glue data catalog, click save, and then when I go back to Athena, if I do my select star again, what we'll see is that that schema is already updated in here. So with TSV, it's pretty easy, right? Because it's just we just renamed the column essentially, and we don't need that header that's in there. So the changes that you make in the Glue data catalog take effect immediately in Athena. And then when Athena runs this select star, what it's doing is it's going out to S3. It is opening this TSV file and then just reading in a sample of that TSV file. That's why when I do a limit 10, it's only reading that 1 megabyte of the file there. So that's pretty straightforward just in terms of the interactions between Athena and Glue. So Athena creates that table in Glue. That table just holds all the references to where that file lives and all that kind of stuff. I could even go ahead and I can say, drop table pain pills TSV. That's just going to remove the table from the Glue data catalog. All the data still stays there on S3, and that's how that works. Now let's look at that gzipped file as well. So I'm going to go back here. I've also got a create table statement for the gzip file, and the only thing we just change the location and add the compression type to gzip. One other thing to call out here, if I look back at my S3 bucket, what you'll see is I've got this I've got two prefixes in my Athena folder here, or my Athena prefix here. I've got the TSV prefix, and there's one file in there. And then I've got my TSV-gzip prefix. And I've got one file in there. And what happens when Athena looks at the glue data catalog says, hey, the data is here. And Athena goes ahead and scans that prefix for files in that prefix. So I can't put these two different files under the same prefix, or I can't point Athena to a specific file, because the way that it works under the hood is it scans that entire prefix and looks for files inside of there that match the schema and the format and all that kind of stuff. So when I create my table here, you can see I just point to that prefix. So I've got my CSV gzip file here. Let's do a select star from that file, and we'll do a limit 10 again. And what we'll see is that should, again, come back pretty quickly. See that came back in under a second. Only scanned 58 KB of data, and there's the data from there. Now let's do a count star from here and see what happens there. So with the previous count star, under the hood, Athena is a distributed query engine. So that distributed query engine is able to open that TSV file in multiple different locations, right? So you've got, one worker that can open and read the first 10,000 records. That's just a random number. You've got another worker that can read the next 10,000. And so Athena can split that up and read that whole 75 gig file in a matter of seconds, right? But with this gzip file, that's not possible because gzip is not a splittable compression format. So what happens is you end up having one worker that's sitting there and trying to g-unzip this entire 6 gigabyte file. Not only is it trying to g-unzip that entire 6 gigabyte file, it's trying to expand it to that full 75 gigabytes and then start doing the querying on it. So this query is going to take quite some time, right? Because you're limited to essentially one CPU core that is g-unzipping that file. And so even though that gzip is saving us space on S3, it's making it more difficult to query because now only one worker can be responsible for that single gzip file. So this is one of those things where you kind of have to look at your data set and say, okay, do we compress the gzip file, or do we compress the TSV file? How big is it? What kind of queries are we going to be doing with it? And that's where you have to be really careful about the different formats and data types that you use. So let me take a brief diversion here and let's talk about binary formats. So I've showed these TSV data sets, right? And these are pretty straightforward. They're human readable. You can open this in Excel. You can slice and dice this on the console. It's really easy to deal with. Well, one thing that people often end up doing is converting these text-based formats to binary columnar formats. So let me switch over to, I've got a Jupyter Notebook here that I'm going to hop into a little bit later when we talk about Spark, but I want to talk a little bit about Apache Parquet. So Apache Parquet is a binary columnar storage format that's commonly used in big data applications. When I initially started working in big data, I had a little bit of trouble wrapping my head around what this meant, just because I'm so used to seeing data in rows, right? Whether it's a CSV, whether it's a relational database, I've almost always seen data in rows. Well, what happens is Parquet kind of takes those rows and flips them on their side and groups them in columns. So let's take this simple table right here. If I want to, for example, count the number of states in this column, what I have to do as a machine, I have to go and kind of look at each row, and you can see the row format here. I have to go and parse through each row and say, okay, here's the ID, age, state. Okay, that's 1. ID, age, state, that's 2. And it has to go through and do this counting through the entire CSV file or TSV file or whatever have you. With columnar formats, what it does is it takes these columns and it splits them up into different chunks. So if I want to go and count the number of states, I can actually ignore the ID and the age data, and I can just go over here to the state data and say, okay, how many states are there? And even at a glance, as a human, I can more quickly see that there's 4 states in there rather than trying to count it in that row format. So that's one aspect of Parquet, is it takes this data, converts it to a columnar format that's more optimized for analytics, right? Oftentimes you're doing counts of columns or maxes or other aggregates of columns. And so that makes it a little bit easier to iterate over just the data that you need. But the other really cool thing that Parquet does is it actually adds metadata. So on this age column, it would add a min and a max and a count. And so you could see if you were trying to take the minimum of the age column, it wouldn't even have to read any data. It would just say, okay, the minimum is 20. And you're trying to do a count, same thing. That metadata is built into the Parquet file format. So the Parquet documentation is pretty good, but this image sums it up. So what Parquet does is it takes those rows, breaks them up into row groups, and then inside each row group it has a set of columns. And then those columns also have pages essentially that it can page through. And then in there you've got your metadata. So the number of values, the min max, compressed size, all this different kind of metadata that is really, really useful. So if let's see, I might have a Parquet file lying around here. I do. Okay, cool. So there's a tool called Parquet CLI. If you're on a Mac, you can just do a brew install Parquet CLI. This is part of the Apache Parquet project, but what we can do is we can actually say Parquet meta, and then we specify this Parquet file. Let me pipe that to less. And so what this does is this gives us a bunch of information about the Parquet file. It gives us the name, what version it was created by. It has the schema built into there. And so there's the schema down there. And then here is all the metadata. So it gives us a row group, the number of rows in that group, or number of records in that group. So there's 300,000 records in that group. And then it's also got the min and max, like I said. So if we've got an integer column down here, you can see there's the min and max of the integer column. And even if it's a string column too, you can have the min and max of the string column. So Parquet bundles a bunch into this file, right? So now instead of opening up a text-based file and doing a count over every single row, I can just look at this metadata and say, oh, cool, there's 300,000 records in there. So that is how Athena can also be optimized as well. I'll show this a little bit later, but I took this TSV and I converted it to Parquet. So let me do an S3 LS of that. And I think that is, where did I put that? There we go. So I have this Parquet, and I took this and repartitioned it into Parquet files. And you can see each of these Parquet files are about 300 megabytes. And let's see how many of those I have. So instead of one giant 75 gig CSV file, I've now got 35 Parquet files that are each about 280 megabytes. So what that means is Athena will be able to do optimized queries over these quite a bit easier. So let me go ahead and create an Athena table over that Parquet data set. And here I'm just doing stored as Parquet. So let's see, okay, we'll do this create table really quickly here. Oh, that count star over the gzip finally finished. That took 6 minutes to g-unzip that file. So, if you have a giant gzip file, you may want to split that up. But let's look at Parquet. So here is the Parquet table. I'm going to create that table, store it as Parquet. If I go back to the Glue console, let me look at my tables really quickly. You can see my Parquet table is now in there. And if I look at that Parquet file, you can see there's the input and output format and the Parquet Saturday. And then down here, I think that's about it that I wanted to show. You can see again, there's where Athena just stores the prefix. So it's going to scan all those files when it does any sort of query. So let me go back to Athena. I'm going to do a select count star from that Parquet data set. So what I do there, I'm going to go ahead and run that query. And what we'll see is that finishes pretty quickly. And behind the scenes, Athena is essentially opening up every one of those 36 files, reading the metadata out of those files, and aggregating that count. And so we can see that ran in 3 seconds, and it only scanned 0 KB. Wait a second, how is that possible? Well, Athena doesn't have to scan any data because it's just reading the metadata. So I could have and I do actually have this, I could have a giant Parquet file, and Athena wouldn't need to read any data from that Parquet file. I've got this singular Parquet file here, and so if I do an ls of that, you can see that's a 3.5 gig Parquet file. So if I actually create another Athena table on that Parquet file, let's do that. Parquet huge. Cool. And I'll do a select count star from that. That's actually going to be even quicker because Athena only has to go and open one file and read one row count. Well, actually, it has to go through the pages in that file and read a bunch of different row counts. But essentially, it has to open one file, read those counts throughout the entire file, and there we go. We've got our count star from that file really, really quickly. So that's where moving to binary formats can really, really help. Don't think there's anything else that I want to cover there right now. I think this is one thing to just call out here. This is where you need to be careful just in terms of like what file formats you select, what you convert them to. There's a lot of work that's done around optimizing your file sizes. So a lot of folks say about 250 megs is a good file size for Parquet files on S3. It depends on your data set, right? So if you've got petabytes of data, you probably want a bigger Parquet file than 250 megs. You might want upwards of a gig or something like that. And that just means you have to balance the number of files and the size of those files. So that's something that is a pretty common data engineering task. So next, I want to show how Spark was going to process this file too. So let me hop over to my Jupyter notebook here, scroll back up to the top, and I've got a cluster in EMR. It's a 10 node C5 4XL cluster. So I went ahead and created that from EMR Studio, and I'll go ahead and make sure that that cluster is up and running. So we have to start a new Spark application. I hadn't quite started one yet. So that's going to go ahead and start up. But what I'm going to do, I'm going to read these same TSV files in Spark. I've got them in a different location. They're stored in the same prefix here in S3. And this works, because with Spark, you can point directly to a specific file if you want to. You could point to a directory or a prefix if you wanted, but you can also point to a specific file. So that's kind of what's happening there. And I'll open up the Spark UI too, just so we can get an idea of what's going on behind the scenes. So let's go ahead and read this giant TSV file. I'll hit enter here. What we're going to do, we're going to read that file. We're going to infer the schema from that file. We're saying that it's tab separated, and we're saying that it's got a header as well. And then we just point to that TSV file. And now if we look at what's happening behind the scenes, we can see that we've got this job 2 down here, and there's 597 tasks in that job. So let me go over here and let's see. Is that application 30? I think that's the one that I want. Yep, that's the one that I want. And let's refresh. Great. So here is our TSV infer, and that's going through and loading. We can see the 597 tasks there. And if I dive into this load stage right here, you can see we've read 75 gigs. So it went and read all of that entire TSV file. And if I look at those 597 tasks, what we'll see is that each of those tasks is reading 128 megs of data. So what Spark did behind the scenes, again, it looked at that TSV file. It said, hey, I can split that up into chunks, and it split it up into chunks of 128 megs behind the scenes. And so when it read that in, it printed out the schema, and that took that took 30 seconds to go ahead and do that, which isn't too bad for a 75 gig file. So we can see that it split that up into those 128 meg chunks and read that in. One thing that is kind of fun, like what happens if we load it without inferring the schema? Let's say we already know the schema, or we know that the schema is all strings. That actually happens super quick. So if I go ahead and do that same load just without inferring the schema, that will finish in about 1 second, or 1 to 5 seconds there. That's because it only had to read the first chunk of that file to get the header names out of the file. So similar to how Athena is only going to scan a portion of the file to read that in, with this TSV no infer here, we only had one task, and all that task did was it just loaded a tiny chunk of the file to see what the headers were. So it only read a KB of the file there. We just had that one task. So pretty tiny. So that's one thing, just in terms of optimizing that you can do. So let's switch back to here. And then, if I do a count here, of that data frame that I just read in, again, we see that we will have 597 tasks. So again, it has to go read in that whole file, do a count over every single row in that file. So the first question is, where does this 128 megabytes come from? Well, that's just a default setting in Spark, right? So the Spark configuration uses this 128 megabyte value as Spark file's max partition bytes. So what that means is Spark will take that 75 gig file, split it up into chunks of 128 megs, and when it does that, it gets 596 point something something, and if you round that up, then you get 597. So that's where the 597 tasks come from, is splitting that file up into the different chunks that it can read. I won't do this here. I've got a bunch of, a little bit of a deeper dive here where I talk about how the executors work and all this kind of stuff, and we can even like tweak and tune that max partition bytes. We can set it to 10 megabytes. We can set it larger. Really depends on your data set. But I want to hop up to, what happens if we have a non-splittable file. And I'm not going to do this because it takes quite a while. But if I want to read that CSV, that gzipped TSV, I can, but what's going to happen is the same thing as Athena. Spark cannot split that gzip into multiple different slices, right? So it has to have one single task that's reading that gzip file. And in this Spark configuration that I have, it takes 17 minutes to go ahead and unzip that. So that is, again, one reason why non-splittable compression formats can be a little bit of a challenge there. Awesome. I dig into a little bit more about executors and cores here, but the other thing that I want to do, I talked about Parquet, and one thing a lot of folks do with Spark is they'll take this and convert their data sets to Parquet, and you can do, you can do that. So I've got an example here. I read the data set from that TSV file, and then I just do a data frame write to Parquet. And by default, we'll see 597 Parquet files. So this is something that comes up pretty often too, where people say, okay, I want to write to a Parquet file. They want to write to a singular Parquet file. Well, that depends on how many tasks or partitions you have in Spark. And one thing you can do is you can repartition your data. So if you know that you don't want these this many Parquet files, what you can say is okay, let me repartition that data. So each partition has a larger chunk, and essentially each executor has a larger chunk of the data, and then write it out. And so what that looks like down here, if I do a repartition 1, that takes all the data and funnels it to one single executor and writes out that one 3.5 gig Parquet file that we saw earlier. But the problem with that is it's funneling it all down to that one executor. So one executor is writing that file, and that's not terribly optimized either, right? So you want to balance between your file size and how your data is read in. In the case of this, I did a repartition to 35, so that took 597 tasks and reduced it down to 35 tasks, and then wrote that out to the Parquet files. So then I only had 35 Parquet files that were around 280 megabytes. So this is something that a lot of folks spend a lot of time doing in data engineering, is taking all this data, converting it into this binary optimized format. But when you do, then Athena can make better use of that, right, when it's doing its queries. Let's do one more count from the Athena Parquet data set, because I want to show you also like how quickly those stats matter. So maybe I want to do like a count distinct from that Pain Pills Parquet data set. Again, behind the scenes, Athena goes, lists that, it's already done, goes and lists that prefix, opens up all the files, reads the header from those files for this count, this aggregate function, and then sums that all up on the back end. So it does this count distinct. It finished in 1 second. It only scanned 200 megs of data. If I go and recreate my my TSV dataset here. Let me recreate this table. Do that super quick. And let me do the count star from this TSV table instead of this count distinct from that TSV table. What we're going to see is this is going to take a little bit longer. Even though that CSV file is splittable, it doesn't have those aggregate statistics built into it. And so, 7 seconds isn't long, but it's much longer than 1 second. And Athena, behind the scenes, it still has to scan this whole 75 gig file instead of 200 megs. So even from a cost perspective, right, Athena charges based on the amount of data you scan. Even from a cost perspective, all of a sudden you've realized a huge cost savings by converting to Parquet too. So that is, I think, all I want to cover today. I hope this is useful. You know, reading data in S3 and converting it and doing all this, Parquet stuff can be pretty confusing. Took me a while to wrap my head around it, but one of the ways that I think about the Parquet file format is it's kind of like a database, to be honest, right? If you look at this notebook here and look at this image, like this is a database essentially. The data is split up into columns. It's got metadata on the columns. There's all sorts of data kind of jam packed into this file. So it's a pretty cool little format. So there's Parquet, there's ORC. And I think these are pretty common. Well, they are pretty common for folks to convert things to, and you can do a lot of optimization with it. So I hope this was useful. If you have any other ideas for things that you would like me to do a little bit of a dive into with analytics on AWS, please comment and let me know. And I hope you all have a wonderful day. Bye-bye.